Hello students, we are starting with a last month crash course for Jee-Advanced 2021. Since the advanced examination is on 3rd October, which is 24 days away, we would like to keep you updated with daily practice problems and some important problems for the advanced examination. We will keep discussing every day. Okay, so this is day 1, and please subscribe to our channel if you would like to watch such videos every day. Okay, every day I'll be taking up 5 problems and giving you suggestions in those chapters. Okay, and I'll be discussing those problems. Let us start with this. So first, today let us discuss the first problem in the chapter of heat transfer. As you can see here, the questions related to conduction and radiation have occurred 4 times in the last 5 years. So radiation, there are 3 questions given, okay, in the last 5 years. So let us look at a question corresponding to radiation. And in radiation, we have 3 major topics. Those are Stephen's law, and second one is Newton's law of cooling, and third one is Wien's displacement law. Wien's displacement law was asked once in the last 5 years, and it's a very simple topic. So I hope you have covered the topic. So now let us solve this problem. Please pause the video and try to solve this problem, and then I will discuss the problem. So hope you have tried. Now, in this problem, what is the concept? So you have a body which is at some temperature of 1000 Kelvin, and it emits radiation. The heat radiation will have all wavelengths, as you know, and Wien's displacement law tells us that high intensity wavelength lambda m follows the displacement law, that is lambda m into t equal to a constant b. So lambda m is equal to b divided by t. Now we have 2 cases. First, at 1000 Kelvin, okay, the high intensity radiation falls on the metal plate. Then the temperature rises to 1289.8 because it increases by this much. Okay, and again the radiation falls on the metal plate. So let us draw the metal plate here. So you have a metal plate here, and which only receives lambda m, the radiation corresponding to lambda m. So there are 2 instances, first instance and second instance. In the first instance, the temperature is, let's say, T1, and lambda m in that case is equal to, let us say, lambda 1. And in the second instance, the temperature is T2, and the corresponding lambda m is equal to lambda 2. Or you can put lambda m dash, no problem. Now, so when such radiation falls on a metal plate, they're asking about Ke of the fastest electron. So the highest kinetic energy electron will have Ke, you know, that is equal to hc by lambda 1 minus the work function phi here. Here, the kinetic energy of the fastest electron will be hc by lambda 2 minus phi. Now they are asking the change in Ke, they are asking the change in Ke, and therefore all I have to do is Ke2 minus Ke1, which is as you can clearly see, Hc by lambda 2 minus Hc by lambda 1. Now, I know that lambda 2 can be written as b by T2 from here, and lambda 1 can be written as b by T1. So this will be Hc by b times T2 minus Hc by b times T1. So the change in kinetic energy which we actually need is nothing but Hc divided by b times T2 minus T1, the change in temperature. So what is Hc? As you know, it is close to 1240 eV nanometers divided by b, which is as given 2898 micrometer Kelvin, and change in temperature is 289.8 Kelvin. So ultimately, the change in kinetic energy which we need will come out to the following. Delta Ke is equal to, so you can easily see that it will be 124 times 10 to the power of minus 3, because nanometer by micrometer is 10 to the power of minus 3. So x that we need is indeed 124. The value of x that we need is 124. I hope you have understood this question. So this is a combination of Wien's displacement law and photoelectric effect, both the concepts. I hope you have understood this. The next question we are going to discuss is on nuclear physics, and we are going to discuss this question on alpha decay. There was a question on beta decay in 2016, but majorly in nuclear physics, the advanced papers contain questions on radioactivity. So you can stress on radioactivity when you are practicing nuclear physics, because in the last 5 years also 4 times the questions were from radioactivity. However, let us today discuss a problem on alpha decay, and you can just pause the video, try to solve the question. Okay, read it properly, then I will solve the question. So guys, here what we have is a nucleus X. Let's say it has momentum P, and after a while the nucleus decayed into Y, which is at rest, and an alpha particle which will have the same momentum P. Why? Because momentum is conserved in all the nuclear reactions that we discuss. So momentum conservation needs that if the momentum of X is P, since Y is given to be at rest, the daughter nucleus is given to be at rest, then we can realize that the momentum P shall be possessed by the alpha particle. Now, the mass of X is 120 atomic mass units. That of alpha particle is 4 because it's a He++, and this will be 116. And one more thing we know is that the Q value of reaction is equal to binding energy of products minus binding energy of reactants. This also we know. Now, what is binding energy of products? It is nothing but 116 times 8.017. This is the total binding energy of the daughter nucleus Y, because binding energy per nucleon is given to be 8.017. And then you have 4 nucleons in alpha particle and binding energy per nucleon is 7 there. So 7 minus binding energy of the reactants, which is 120 times what is given 7.5. So this is the Q value of the reaction. Now energy is also conserved in a nuclear reaction. So energy conservation requires us to conserve the mechanical energy before the reaction plus the energy liberated in the reaction shall be equal to the energy after the reaction. So here I want you to be cautious. Binding energy is as such not an energy. Okay. If you are increasing binding energy, it means the potential energy is decreasing. Okay. The nuclear potential energy is decreasing. So those of you who would like to equate the energy before and energy after, you better equate the kinetic energy plus mass energy before reaction and kinetic energy plus mass energy after reaction. But binding energy plus kinetic energy, that cannot be conserved, because binding energy is the amount of energy required to break the nucleus. It is not the energy possessed by the nucleus. Okay, so please do understand that. But in this question, we will do it much easier manner. We simply say the kinetic energy before the reaction plus whatever energy is liberated in the reaction shall be equal to the kinetic energy after the reaction. So before the reaction, P square divided by 2m, if the mass of this is m. The mass of X is m, its kinetic energy is P square by 2m. And you can easily see that mass of alpha particle will be m by 30. Okay, so the initial kinetic energy of X is P square by 2m plus Q value of the reaction is equal to the final kinetic energy, which is P square upon 2 times m by 30. So this implies that 29 times P square by 2m, which is the initial kinetic energy which we require. In the question, we are asked to find out initial K of X, which is nothing but P square by 2m. That is equal to Q value of the reaction. So the initial kinetic energy we need, P square by 2m, is nothing but Q divided by 29. If you solve this properly, if you do this calculation properly and then divide it with 29, you will get close to 2 mega electron volt. Okay, it will be 1.999. So the answer is either 1.999 or 2 mega electron volts. I hope you have understood this. Please read this question from surface tension. And as you can see above, there are many questions on surface tension chapter in the last 5 years. And mainly capillary rise is a major chapter, major topic. And excess pressure, surface energy, there were questions on these topics also in the advanced examination. So please concentrate on these topics. And let us now solve this question. You may please pause the video and try to answer it on your own. So here, what is happening? Let us try to understand. We have, let's say, a container, and there is some liquid in it. or simply water in it. Now, what we have done, we have a long capillary tube which has been submerged into it. So now when it is open, as you know, the water will slowly rise inside the capillary tube because of surface tension effect, and there will be some meniscus that will be formed here. So you know all these things. Now what they are asking out of us is that the upper end of the capillary tube is sealed and outside pressure is the atmospheric pressure, that is standard pressure. To what length we should submerge the capillary to make water level inside and outside coincide. So what we are going to do, we are going to submerge the capillary but before that, what we should have done is we should have closed the tube. So please understand, the tube is closed and then we submerge it. Now here the question is little unclear whether the tube is closed after the capillary rise takes place or before it. It will be difficult to solve this, okay, if it is closed after the capillary rise, okay, if such a thing is given to us. So let us assume that it is closed from beforehand. So there is nothing here. I'm sorry, just a moment. Yeah, there is nothing there. Please understand. And so the length of 110 is at atmospheric pressure. Now you have submerged it. So x length has gone into the water. 110 minus x is outside. And here there is some capillary effect which we cannot neglect. Okay. So let us now do this question. Here the pressure is P0 and just below the surface here also the pressure must be P0, because inside the liquid at the same horizontal level the pressure shall be same. The only reason why we can have a different pressure here is because of the surface. Now let me draw the surface neatly for you. So the surface will be something like this. Okay, the surface here is something like this. Okay, I hope you understand that. Now here if the pressure is P, here the pressure will be P minus 2s by the radius of this meniscus, because it's a spherical surface, and in spherical surface from concave to convex there will be a drop in pressure of 2s by r, whereas from convex to concave there will be an excess pressure of 2s by r. So actually the pressure in the reduced column of 110 minus x is nothing but P0 plus 2s by r. P0 plus 2s by r. So now it is very clear. We can use P1 V1 is equal to P2 V2 because we don't think the temperature changes, and that's why 110 minus x into the area, that is the volume, into pressure, which is P0 plus 2s by r, is equal to 110 into area into P0. So from here we can get x, which is the submerged length. So as you can see here, 110 into A into P0 gets cancelled anyway. So we get XA P naught is equal to X, one moment, XA into P naught plus 2S by R is equal to 110 into A into 2S by R. Yeah, this is what we will get. So X is nothing but 110 into 2S by R divided by P naught plus 2S by R. So from this, you can easily solve the question. I hope you have understood this. In water, contact angle is 0. So R is nothing but D by 2. The radius of the meniscus is also radius of the cylindrical tube. So R is nothing but D by 2. So if you substitute that and the value of surface tension for water, then you will get X in millimeters. And P naught is 10 power 5, as you know. I hope you have understood this. Our next question is on sound waves. And as you can see, many questions are given in this chapter in the last 5 years advanced papers, mainly Doppler effect in beats. Doppler effect and beats is a very important topic. Resonance column, the question was given only once, and organ pipe also once. So we will be solving a critical question on resonance column today. So please read through this question and try to solve it on your own, and then I will solve it. So I hope you have read the question. It's a simple one. So after some time, the level of water or the liquid in the column decreases by 21 centimeters. No, the reservoir is lowered by 21 centimeters, they say. So there is a difference between by how much the level of water decreases in the column and by how much the reservoir is lowered. So let us try to address this main concern. So all of you please concentrate. Always remember one thing about resonance column. The level of liquid in the reservoir as well as the column, both shall be same. The level of the liquid in both shall be same, because the topmost portions of reservoir as well as the column both shall have the same pressure, and that is why the level of liquid in both must be same. Okay, so now let me draw the whole thing properly. So what I am trying to say, please try to understand well. So here the reservoir has been lowered by 21 centimeters. Okay, so suppose the air column in the resonance column, okay, the air column length then becomes y. Okay, why it is not 21? That is what we need to address. Okay, so the original level of liquid in the reservoir, let it be somewhere here. Okay, and that has been, the original level has been lowered by 21 centimeters. Actually what it means is the original level of the liquid in the reservoir will be on par with the top edge of the resonance column. And if you lower the reservoir by 21 centimeters, okay, in order to match the levels in both the resonance column and the reservoir, okay, what will happen is what we are going to see. One moment, I will correct the picture a little bit. I am sorry. Okay, so don't worry about minor corrections. Now guys, please look at this. So the level of water at any time in the resonance column as well as the reservoir shall be same. This is one important factor. Now I said from the original level of liquid in the reservoir column, that portion has been lowered by 21 centimeters. But the free surface of the reservoir will be somewhere else. Why? Because the liquid that has been replaced in the reservoir, the resonance column, will come down into the reservoir and it will occupy this volume here. So what we can say is that if this volume is transferred back into the resonance column, it should fill all this Y. I hope you understand that. So what I mean to say is that Y times the area in the resonance column is equal to 21 minus Y times the area in the reservoir. This is the crucial equation. And therefore, we will realize that Y times AC is equal to 21 minus Y times 6 times AC. And accordingly, we get 7Y is equal to 21 into 6, or Y is equal to 18 centimeters. Okay. So the first resonance occurs when the air column length is 18 centimeters. Okay, 18 centimeters. Then we are lowering the reservoir further by 49. That means we are lowering a total of 70 centimeters. Again, the air column length Y dash that time will simply be 70 into 6 by 7. In the same way, we have made arguments in the first case, we can make arguments in the second case also. And we realize that when the air column length is 18, there is a resonance. And when air column length is 60 also, there is a resonance. Typically, when there is no end effect, when there is no end correction, we know that first resonance length and second resonance length shall be in the ratio 1:3. But it is not so here. And therefore, there is some end correction. We don't need to calculate it, but we know that the consecutive air column lengths L2 and L1, if they are corresponding to resonances, then L2 minus L1 must be lambda by 2. This is a very standard equation in the resonance column experiment. So in our case, Y dash minus Y, that is 42, this is lambda by 2. And lambda is nothing but V by F. So lambda by 2 is V by 2F, which is 42. And therefore, V is equal to 84 times the frequency. But 84 is in centimeter. That's why we have to put 10 power minus 2. And accordingly, if you substitute F equal to 400, you will get the speed of sound to be 336 meter per second. So let me quickly revise the concept. Always understand, okay, in the given picture also there is a bit of mistake. Always understand that the level of liquid, the free surface, okay, in the reservoir as well as resonance column, always shall be at the same horizontal level. As you lower the reservoir, to match the free surface level, some liquid will go from the resonance column into the reservoir. And that is why the length by which you lower the reservoir and the air column length in the resonance column may not be equal, Okay. So you have to compute the air column length by understanding that the liquid or the fluid that has gone away from the resonance column occupies, okay, the some volume in the reservoir. And so you take a reference mark on the reservoir. The reference mark here has been lowered by 21. Okay, but the free surface in both, okay, is not lowered by 21, but something less. It is lowered by only y. So you can say that the fluid which was in the y length of resonance column has been moved to 21 minus y length of the reservoir. And by doing volume conservation, we can get the value of y in the first case where it is lowered by 21, and in the second case where the total lowering is 70 because it is lowered further by 49. And accordingly, we can find the two air column lengths in the resonance column, okay, for which the resonance occurs. These are consecutive resonances, and that is why L2 minus L1 can be equated to lambda by 2. And doing so, we can easily get the speed of sound. I hope you have understood this. Let us move to the next one. There are many questions on capacitors asked in the previous advanced examination, but RC circuit is a separate topic. And in the last 5 years, twice there has been questions on RC circuits. There can be questions on RC circuits this time also. So please revise this topic well. So let us do this problem. First, you guys please read through this problem and try to solve it. And then I will discuss. Here it is given that the switch is on 1 furlong. Then, as you know, the charge on this capacitor will be CV. Okay, that means the plates will have CV minus CV. And we are connecting that to this capacitor, okay, by changing the switch to 2. Now we know that the second capacitor, the outer surfaces will have half of the total charge each, that is CV by 2 each. And that is why inner surfaces will have CV by 2 and minus CV by 2. That we can get by conserving the total charge on each plate. So even at a time when you are just changing to the position 2, the second capacitor has an inner charge of CV by 2. And it is always the inner surface charge on a capacitor that will govern the potential difference, but not the outer surface charge. So you can safely think that our capacitor initially has CV and it is connected through a resistance to R to a capacitor that has CV by 2 charge. Okay, because outer surface charge don't really matter. Now, as you know, over time, current flows from one capacitor to another capacitor. So charge on the first one will decrease, second one will increase, and at steady state, the voltage across each capacitor will be same. And so it is evident that even the current through the resistance 2R will decrease over time. And since the first capacitor is giving out charge, its voltage also decreases with time. So the current from the current through the circuit is highest at immediately after shifting the switch, and voltage in the capacitor is also highest at the time we have just changed the switch position from 1 to 2. So maximum power, you don't need any mathematics, okay, to get this maximum power. Maximum power will be at T equal to 0, or maximum power, okay, will be delivered just after S is changed to 2. because as we know, over time, the charge on first capacitor, that is the one on the left side, let me call it as first capacitor, and this is second capacitor. The charge on first capacitor is going to decrease and the inner charge on second one is going to increase. And finally, the voltages of both capacitors will be same. Okay, so it is evident that charge on first capacitor is going to decrease with time, okay, after you change the switch to 2. And when you write the Kirchhoff's loop law, the potential gain across the first one, that is V1, minus I into 2R, minus the potential drop across the second one, that is V2, equal to 0. So V1 minus V2 by 2R will be your current. And initially, V1 is highest and V2 is lowest. With time, V1 will decrease, V2 will increase, and finally V1 minus V2 will become 0. So the current keeps on decreasing with time, and the voltage across first one also keep on decreasing with time. So they have their highest values initially, immediately after the switch is changed to 2. And that is why the maximum power delivered will be at the very instant where you have connected the switch to 2. At that time, okay, V1 is V and V2 is V by 2. And therefore, current is equal to V minus V by 2 upon 2R, which is V by 4R. And voltage across the first one is V that time. So max power delivered by the first capacitor is nothing but its voltage V into V by 4R, which is V square by 4R. Okay. So that is about today's session, to expose you to some good problems and their solutions. I hope you like it. Please subscribe to our channel so that we can keep posting more such videos. We are planning to post such videos every day based on your cooperation. Okay, it is all free, but please do subscribe to our channel and share it if you like it. Thank you so much, students.